Mehranfar from the Technical University of Munich, and I'm very happy to present the research on developing a hybrid bottom-up top-down AI method for improved digital twinning of the building using point cloud and RGB images. Today, BIM and digital twin technology have become a transformative tool in the AEC domain by providing different opportunities from the design and construction to operation of maintenance of the building. And of course, they have a lot of potential application for facility management, operation maintenance, sustainability, and many, many more use cases. Actually, when we look at the digital twin and BIM technology in more detail, we will see that at the core of these advancements lie in the utilization of the digital building model that reflect the physical structure of the building. This digital building model integrates all the geometric and semantic information regarding the building physical assets, and actually this is a bridge between the physical realm and digital counterpart. This digital building model can be created through different ways using manual process, technical drawings that usually present as design aspect of the buildings, and also rescan to win, which recently knows as an effective way to convert laser scanners for light and like point cloud and also RGB photogrammetry images to the, let's say, digital building model using, let's say, automated or semi-automated methods. To have a look at better understanding about the scan to BIM process and how it works for creating the digital building model. In the practice, the digital building modeling of the buildings encompasses three main steps: pre-processing, which means that make the data ready for further processing, coming with the noise reduction, subsampling, or maybe separation different flow between the point cloud data. And then we have the semantic enrichment, which is about extracting some meaningful information for the data to make it readable for the human and machine interpretation. And finally, we have the geometry provision, which is about the representation of the geometric digital building model based on the use cases that we have, based on the level of development for the object of interest. Well, currently in the literature, most of the developed method for creating the digital building model from the point cloud data and RGB images are mostly based on the data-driven, bottom-up or top-down-driven, model-driven, and also AI-based solution. Despite all the advancement and then contribution they have made in the field, the most of the development method is still struggling with some challenges come from the nature of the point cloud data. Due to the presence of the noise of gap and clutter that comes from the different object, the method is really sensitive to the quality of data. That means that the result digital building model can represent inconsistent geometry and represent inaccurate parameters value. That means that this method is mostly, let's say, case-oriented from the different data to different data. They need to adjust the parameters of the algorithm for a better performance, and it actually reduce the level of automation and, of course, hinder its application for scalability. To address these challenges, here we propose to use a hybrid bottom-up top-down AI method for improve the digital twinning of the building from the point cloud and images. And the idea is to use domain knowledge in design and construction of the building with the AI capabilities in sound understanding within the point cloud and RGB images to create the digital building model first with the rich semantics and also the consistent geometry, coherent geometry. For this, what we have proposed is a pipeline that integrates the three main steps. First is the semantic enrichment. The second step is about creation of parametric digital building model. And finally, it's about door and window detection to improve the level of development in the final digital twin model. Let's start with the semantic enrichment, which we first use a pre-trained point transformer network to assign the semantic label at the point level to the data. And the objective of this step is to just first of all extract the main structural element of the building within the point cloud, including wall, ceilings, and floor, and then using this information into a data-driven, let's say, a 3D space parsing step that allows us to actually automatically partition 3D individual spaces within the point cloud data, which of course provide valuable information about the current layout of spaces within the environment. And finally, for this step, we have another bottom-up approach that allows us to use the principal component analysis to let's say, effectively consider the neighborhood of the points, and then individual wall instances are separated based on the orientation of the environment into three main categories of elements, let's say horizontal, vertical, and inclined groups. In the next step, all the semantic information comes from the semantic enrichment steps are used through the data-driven or different model-driven approach to create the first floor plan mask of the environment that actually represent the current position of the wall and layout spaces. But as you can see here in the figure, so most of the methods usually use a local model fitting. That means that they use a traditional methods like ransack plan fitting or less square model fitting to find the, let's say, local position of the wall and then insert them to create the 2D floor plan mask, and this model can be extruded into 3D. But actually, these methods actually depend on the quality of the data and then in the presence of the, let's say, noise and gap, and also, let's say, over-segmentation. They may result in creating of the floor plan mask with inconsistent geometry. What here we have proposed is to use a global optimization through the parametric model fitting. We use the domain knowledge in design and construction of the building to design a parametric system for the floor plan by considering roles and dependencies between different parts of the system, and then use the meta-heuristic optimization to fit the entire system of the digital, let's say, floor plan mask into the point cloud data. As you can see here, and then compare it between the initial floor plan mask created using the data-driven approach and then, let's say, optimized one through the global optimization, the result comes with the consistent geometry. Of course, in this step, we consider the 3D volumetric model and every parameters of the model, considering the geometry, also location of the elements, we optimize. In the next step of the proposed method, we are aimed to improve the level of development by detection of the door and window and attaching them to previous model. Here you can see the result of point transformer semantic segmentation on the point cloud data. And as you can see, due to the reason, like say, the geometric feature similarity between door and window instances with other building assets, and also the noise comes from the reflection of the laser beams from these surfaces, they comes over with the over-segmentation that result in accurate parameter estimation within the point cloud. What we have proposed here is a novel approach to actually detect the door and window instances from the images. First of all, we consider that each point belong to each wall instances after fitting the parametric model in the previous step are projected into vertical plan, let's say XZ or YZ, and then we convert 3D representation of the point cloud into 2D raster images using a grid sampling method. Next, we consider that we can use an AI object detection based on the yellow weight object detection model. And for this, we need a data set that, of course, we captured a lot of images from different buildings in the Technical University of Munich and building around, which this data set encompasses and consolidate all the images from different door and window instances with different materials, different shape, different lighting condition, and different state of closed, semi-closed, and open position. Then we train the model and test it on the data. And here you can see the comparison between the result of the semantic segmentation of the point cloud and detected door and window on the projected wall point images. It's worked really well, but still it has an issue. That's the mapping between the 3D space into 2D spaces always comes with an error in estimating actual dimension of these bounding boxes, let's say elements in 2D spaces. What we have considered now is a post-processing step. So basically, we have gathered a library of parametric door and window families based on the BIM standard project. And after detection of the door and window instances in the images, the closest model from the library of parametric model of the door and window is called, and the actual parameters is replaced with the detected bounding box dimensions. So this step actually adjusts the error, and also it improves the integrity of representation for the final digital building model. So to evaluate the performance of our hybrid bottom-up top-down method for digital twinning of the building, the algorithm was tested on different point cloud data from the Technical University of Munich and then some office buildings from the companies. And here the method can achieve an overall accuracy of about 90% for the semantic enrichment, and that means that it can assign the semantic labels to the data and different levels like spaces, point, and wall instances. And it can create a geometric digital building model with 6 centimeter accuracy in the term of location of the element and also the actual parameters of them. So coming to the conclusion, well, in this research, we try to use domain knowledge in design and construction of the building with the AI capabilities in the understanding within the point cloud and images to improve the digital twin building model and creating building model with consistent geometry and rich semantic information as possible. Of course, with a lot of contribution that we have, we still have some challenges that first, The proposed method for the door and window detection can only detect the rectangular shape, let's say, door and window instances, and for the round geometries, so we need to use the pixel-wise semantic segmentation in 2D images. And of course, the method cannot be applied on the building project that constructed by mirror and glass material. So with that, I would like to thank the TUM GNI for supporting us to conducting this research, and thank you for your attention. I would be happy to answer your question.